right? So remember, I had to apologize, but there is no class this Friday. So this is the last class of the week. Okay, so no class this Friday. Actually, no nothing this Friday, apparently, okay?
Will campus be like closed?
I believe so. It's an in-service, it's an all-staff in-service, so, which I'd rather be teaching, but they didn't ask me. So I brought this up because you guys know that we've got some warm temperatures coming.
65 degrees.
Woo!
Well, what's that?
Really?
Friday-ish, maybe kind of segue a little bit Saturday or Thursday. But yeah, basically we have warm air that is pushing up and from the west to the east, and that's what's going to get us. This kind of the cold temperatures we see now, feel now, is actually part of cold air that came down. Okay, yeah. So one of the things that I think is interesting is this is the National Weather Service. This actually is in telecast, which I also like, in telecast.com. And it's just up to whoever does those fronts who gets to decide how they want to draw the fronts. So in this case, notice that they did not draw kind of the clear warm front and cold front. They drew what's called a stationary front. So this alternating red, blue, that's a stationary front. Basically, we have warm air towards the south and cold air towards the north. A stationary front, the cool thing about it, no pun intended, is basically it's a standoff between those two air masses. Okay. So those are those two things. One of the things that I kind of pulled up today is at the National Weather Service, you can kind of go into it and find your way to the Storm Prediction Center. This is not the Storm Prediction Center. This one is, nope, this one is. Okay, so actually people that put out our forecasts are, you see SPC, those are the folks who put out our forecasts. You might have heard this if you've got like a weather, what do you call it, weather
radio.
Yeah, if you have a weather radio, sometimes they will say what the discussion is, and actually you can go on the internet and kind of see how they're discussing what elements are happening in the atmosphere. We have one person who went to the spotter training yesterday,
Yeah, that was awesome.
and it was great. So if you get a chance and you want to get credit, I think to get credit after you attend it, you only have to do a paper that's 100 words long, double-spaced typed.
So the guy from St. Louis that came and talked, and then the guy from I think KHQA, who's the newscaster, he talked a little bit too. So we're just kind of discussing the formation of thunderstorms.
Yeah, it's all about severe weather, right?
Yeah.
Yep.
Talked about the supercell, which is pretty common. And then
Yep.
where the cells like line up.
Yeah, yeah. So if you're into severe weather, and honestly, it really kind of helps you when we get to that unit too. So.
And how to identify like if it's a funnel or a tornado.
Mm-hmm.
A lot of people think like it's
Some kind of practical things. So yeah, I think spotter training is good. It's put on by professionals, very visual. Question and answer time. How long did it take when you?
It was from
Couple
6:30
hours.
to about 9.
Wow, about 2.5 hours.
A little bit longer than
You had a bonus. You had a meteorologist there. I mean, well, I had a meteorologist, but not like the news guy. So
Where is it?
it's pretty
It was
cool.
in Canton at Culverstock,
Yeah, this one, but now they'll be having some other ones.
Burlington.
Yeah, one at Burlington, and I kind of put a link up to where the others are. So let me know if you have a question about those. So, yes,
So
ma'am.
we don't have to go to Iowa City for those? We could do any of them?
Yeah, you can do any one. Yeah.
And we get
Yeah.
credit how?
It's in my syllabus, but basically you'll write it up, at least 100 words of what you saw. Yep. So it's time well spent. And yeah, so
I thought we had to go there.
to Iowa City,
Yeah,
no,
I thought
yeah.
that's what you were asking. I'm
Nope,
sorry.
you get to pick any of those locations.
Okay.
So, yep. So we're going to pick up here And remember on the board, I put ELR, I put varies, remember that's the weather balloon, and we learned it in Unit 1, 6.5 degrees Celsius per kilometer. That's the cooling rate of the atmosphere. That varies. Like I said, I'm going to have to revisit that. I put DAR, dry adiabatic rate. Dry adiabatic rate. You probably put DAR at the top of the slide. That actually is when your chunk of air is getting bigger as it rises, and we're going to talk about how do you get a chunk of air rising here in a minute. But it will cool 10 degrees Celsius for every kilometer it rises because it gets bigger and bigger and bigger. Now that one is set in stone. This one is set. Okay. Dry adiabatic rate. So these are two kind of rates we have going on in the atmosphere. So we spent some time in Chapter 4 talking about how cold air holds less water vapor than warm air. So the thing about this chunk of air that's rising and expanding and cooling, honestly, if it cools to the temperature, what we call the dew point temperature, if it cools to reach saturation, then you can have condensation happen in your cloud. And you think, well, what would that look like? Well, basically, that's gas going to liquid. Okay, so condensation, gas going to a liquid. A lot of times, your clouds have flat bottoms, especially if they're kind of newly developed clouds. I don't know if you guys have noticed that. But that flat bottom, I'll draw a little picture here. Okay, if this is kind of the Earth's surface, and basically you had a chunk of air rise, and at a certain, see, I'll do it this way. Actually, we're going to have some nice, better figures than this. It got bigger and bigger and bigger. It got cooler and cooler and cooler. And let's just say right here that the water vapor in there cooled to the point of condensing. So if that's the case, here above that line, we have condensation, and I'm going to go ahead and draw a cloud. It's not a very pretty cloud. But that is my cloud. That is basically where we have, I'll put an L for liquid. Basically, your water vapor has liquefied at that elevation because it cooled. Okay, so it rose and expanded and it cooled to the dew point temperature, kind of at that elevation. Okay, so that elevation, okay, I should say that level, actually we call that the LCL. Lifting condensation level. Okay, so lifting condensation level. Cool. Now we get a few figures, I think. Oh, yes. But before I go on to a figure, here's the problem. It's not really a problem. But we spent some time in Unit 1 and now in Unit 2 talking about as water vapor goes to a liquid, actually energy is released. We call that latent heat. That was one of the terms on your Unit 1 exam. So energy is released, and so during the, if you go up to, and I can't bring it back again, but if you go up to, maybe I can, where that cloud was. Okay, this cloud. You go up to where your cloud is. I know.
Really fast.
I am drawing really fast. I'm just rewinding. Okay, up there where I see the liquid right there, okay, that actually is going to get a little bit, I'm going to go ahead and say warming. Okay, the whole idea that the water is going from a vapor to a liquid, it releases energy. And so actually, then comes this other rate. And this is called the WAR, the wet adiabatic rate. So I'm going to go ahead and under my DAR, put my WAR. Stands for wet adiabatic. Remember that means what's in a parcel stays in a parcel. Adiabatic rate.
Bless you.
Bless you. So assuming, and we're going to talk about how do you get a chunk of air to rise, but assuming your chunk of air is still rising, okay, then actually because there's a little bit of heat, I'm going to put latent heat. Okay, because the wet actually is talking about condensing. Condensation is occurring. So instead of cooling at 10, now it cools at 5 degrees Celsius per kilometer, assuming it's still rising and expanding. So that's kind of what we have going on. The wet adiabatic rate
Per what?
per kilometer. It's the same as those others.
So all three of
Oh,
these,
okay.
those are as you go up?
Yes, this is, all of these, well, this one, yeah, as you go up, but this one is a weather balloon. And these are actually set, these are both set as you go up. And this is assuming your chunk of air is rising. Okay? Chunk of air is rising. This one, actually, didn't mean to kind of throw you off. We'll be looking at environmental lapse rates, but this is the temperature of the environment. This is the environmental. This is the temperature of the environmental lapse rate. You get with a weather balloon. Okay? So I like the diagrams we have coming up, and I think you have some homework questions that are, you might have heard me talking, we're not gonna get through chapter 4 today, so that means chapter 4 is gonna hang on just a couple slides probably into Monday's lecture. So chapter 4, I'm doing that on purpose, so I don't have to grade them as early as I did.
You mean your 3-day weekend?
Yeah.
Yeah, I understand.
Chapter 4, then we'll be doing Wednesday. But, okay, so let's look at, I really like this. So can you guys see what your author has done? Can you see kind of some clouds here, right? I've kind of hidden some things, but you can see it on your slide. So about actually 3,000 meters, which is 3 kilometers, you actually kind of see some condensation happening. So let's look at this little parcel of air, okay? So this little parcel of air is going to rise, and at first it's going to, there's no condensation. There's no condensation for the first 1, 2, 3 chunks of 1 kilometer. So it's going to go from 32 to 22, and from 22 to 12, okay? So what you just saw is this, okay? And actually, from 2,000 to 3,000 kilometers, there's no condensation either. So it looks like it's going to go from 12 to what, 2, right? And then on the figure, you can see some kind of clouds. So actually, if you had a question like this, you would tell me the lifting condensation level is an elevation of, what do you think? 3 kilometers or 3,000 meters. Yep, that's the LCL. Cool. Well, now instead of cooling at 10 degrees, it's going to cool at 5. So 2 minus 5 is -3. Okay? And that's exactly what you see. And then it's going to cool when it goes from 4,000 to 5,000, condensation still going on. And it's going to cool another 5 degrees, which makes it -8. So that's how that whole thing works. Okay, it's kind of cool. Any questions? Because we'd be kind of doing a few more figures like this. Now, I don't know if well, I'll just wait for my slides to explain it. Okay, so how do you get a chunk of air going up? Because if you can get a chunk of air going up, it's going to expand, it's going to cool. If it's dry, it's going to cool 10 degrees Celsius for every kilometer it rises. If you have condensation happening, it's going to cool 5 degrees Celsius for every kilometer it's rising. Well, how do you get it rising? Well, there are 4 what we call lifting mechanisms. How do you get a chunk of air rising? And we'll talk about each one of them. Okay, but I'll talk about each one of them individually, but orographic lifting, the emphasis on the word mountain there. Frontal wedging, emphasis on the word front. Weather fronts have a lifting mechanism. Convergence. If you know what the word converge is, you'll probably do pretty good. Convergence, if something converges, a bunch of stuff meeting there, yep. And actually, this last one, didn't we talk about convection? Okay, yeah. So localized convective lifting coming up. So starting with orographic lifting. You need that one? Oh, sorry. So how do you get a chunk of air rising? Starting with orographic lifting. That involves a mountain. And we said here in North America that basically we kind of have a prevailing what we call westerly wind. Okay, so if I grab the globe over here, you guys would say we have a wind blowing off of the Pacific onto the coast. Prevailing. Now, is it always westerly? No. Okay. But because of that, the way orographic lifting works, and you can see the figure coming up, but basically, if you have wind blowing air, okay, against a mountain, it will not blow the air through the mountain, so it has to go up and over. That's orographic lifting. That's just it. Okay. So what happens, what can happen, is as it rises, it will, the chunks of air will get larger, and as they get larger, they will cool, and you can basically lift to the lifting condensation level, or cool to the lifting condensation, cool to the dew point temperature, and it can dump its precipitation on this side, and it won't have any precipitation. It'll be dry when it comes down the other side. Okay, so we kind of are setting ourselves up for, with orographic lifting, we can have a wet side of the mountain and a dry side of the mountain. Okay, the wet side of the mountain is basically where your chunk of air has gone up. It's cooled to the dew point temperature and it drops its precip. On the other side, okay. In fact, and this is actually a player in some patterns, this chunk of air, if that chunk of air that's at the top of the mountain who dumped all its precip, if it's ready to go down, if it's ready to actually fall down on the other side of the mountain, think of that chunk of air falling down. And one of the things we actually said in the first slide today we opened with, that we covered actually on Monday, was if you take a chunk of air and you make it go down, it will get smaller and it will get warmer. So not only is that on the leeward side, not only has it dumped its precipitation on the windward side, but it's also getting hot. Okay, so hot, dry, desert. Okay. So that's orographic lifting. Mountains can do that. We'll be definitely talking more about weather fronts. I heard somebody say, I'll put this whole slide up here. I heard somebody say with cold fronts we can actually have storms. A lot of times we do have, the blue with triangles, those are our cold fronts. The red with semicircles, those are our warm fronts. You can have precipitation with both types of weather fronts.
What about stationary? Yeah.
Stationary fronts, you can have what's called, you won't have storms, but you can have precipitation usually on the cold air mass side, because it's called overrunning, where the warm air goes up and over. So I like the next slide that kind of shows you a couple of air masses meeting. Okay, again, we'll talk more about air masses and weather fronts. But what a weather front is basically the line between two air masses. So if this is air mass, this is a warm air mass. This is a warm air mass, this is cold air mass. Right here is a weather front. And you're like, well, is it cold or warm? Well, it depends on whether my warm air is being aggressive, and then it's a warm front, or if my cold air is being aggressive, and then it's a cold front. Okay, but that's so just shown up here, and one of the things when we talk about weather fronts is that you probably know that cold air kind of settles and warm air kind of rises, and that actually has to do with the density. So with that in mind, we kind of see cold air masses are kind of like your scrubbers, they kind of like hug the ground. Your cold air masses are like, okay? And if they're like going next to into a warm air mass, that warm air mass kind of goes up and over. Okay, so it's kind of like a steam shovel. So that's actually kind of been what's shown here. Okay, so that's frontal lifting.
So when you have a tornado, which one is overpowering?
So tornadoes come from thunderstorms, and thunderstorms are most likely to form when you have a cold front. So you have a cold air mass hugging the ground. You basically have a nice, abrupt sort of lifting going on there. And that's what gives you your instability. We'll be talking more about that to create your storm clouds. Yep. Yep. Okay, so that's two. Another way is convergence. And I kind of told you, if you emphasize the whole, if things converge at a certain location, okay, they kind of pile up. Sometimes I like to talk about convergence, like if you were on a playground full of kids, let's go K through 3, and you have a bag of candy. Maybe it could be a piñata, something more organized, but basically they're randomly, and then you throw the candy, and they're all going to converge there. Okay, yes, go get the candy. So as they converge there, basically they create a high situation, what we call a high pressure, if that's air. And then what's going to happen is that air is going to go up. Now the kids can't go up because they can't float because they're not like Maharishis or anything like that. But if they could pile up, they would, and if there was candy up there, they'd probably figure a way to pile up and get the candy. So that's kind of convergence. We kind of have, or we can definitely have convergence on the Florida Peninsula, or Panhandle, or no, that's Texas Panhandle, the Peninsula of Florida. This convergence actually is when air goes from smooth water to rough land. It's kind of like if you were skating, I haven't done it forever, but if you were ice skating, you know, what happens if you go from the ice to the land? You go, yeah. Okay, you stumble, yeah. You kind of squish up. And so actually that's another way of convergence. That actually we can have lifting going on there too. So the last one probably looks familiar. Okay, we talked about how you guys know on a sunny summer day, if you wear something dark colored, you are going to absorb more heat. Okay, you have a low albedo. Okay. So actually kind of showing this scenario from left to right, you can have a plot, okay, that's a little darker than its surrounding. That means that you see a little chunk of air, a little parcel of air, gets warmer than its surroundings. And actually that leads us to one of the main players in severe weather is that chunk of air warmer than its surroundings? Okay, if that is, this is actually kind of showing you kind of an unstable situation. Air that wants to rise is actually potentially unstable. Okay, so we have a chunk of air rising and it's getting larger. Okay, and it actually, in this case, it got larger and cooled to the point of within that chunk of air reaching the dew point temperature and became saturated, and we have a cloud formed. So localized convection. All right. So as far as warm air rising, kind of like I showed you with localized convection, the warm air that's being emitted out a smokestack of a factory is warmer than its surroundings. So this is warm. Why? Because it's been processed here, and this is cool. So this is going to go up. It's less dense. Going back and forth right now anyway, in the last, say, month or so, seems like I oftentimes near Fort Madison see eagles right now. Eagle days? No. But birds can actually not catch the pollution thermals, but catch the kind of the pockets of air that are rising and soar. Okay. So the way hot air balloons work, and maybe you know maybe even better than I do, but they're just simply have a place there in each one of these little, looks like a big one, okay, where they are heating. They have a heating element, usually fire, and they're just taking regular air and they're heating up. And now with that warm air, since it's warm in there, basically it's less dense than the air around it, and that is the mechanism by which that chunk of air goes up. Okay, so that's pretty cool. So keep that in mind as we look at the next few slides. Okay. Oops. Did I miss one? No. Okay. So with the localized convective lifting mechanism, I kind of told you that chunk of air is what we say unstable. Why is it unstable? Because on its own, it doesn't have a mountain to do it. It doesn't have a frontal wedging to make it happen. On its own, it wants to go up. That's unstable. Okay. Stable air is air that doesn't want to go up. okay? Stable air then, in the sense of its environment or surroundings, would actually be more dense or colder than its environment. A chunk of air is unstable if it's warmer than its surroundings. Okay. So, we're going to talk about the atmosphere either being absolutely stable, the atmosphere either being absolutely unstable, or the atmosphere being conditionally stable. And I'll warn you right away that absolute stability, I sometimes call it absolutely stable. Because, I don't know why. And absolutely unstable, I call absolute instability sometimes. Let's see. The last one, conditionally stable, that's probably the only thing I call it. So I'm going to try to convince you that I'm going to put ELR over here. ELR. You're like, what is the ELR? I'm like, oh yeah. Okay, what my weather balloon says. What my weather balloon says will dictate whether it's absolutely stable. What my weather balloon says is the pattern of the temperature going up. It will dictate whether it's absolutely unstable. And for this last one, I'm going to put ELR and moisture. Okay. So the environmental lapse rate and the moisture content of the chunk of air that's rising will say whether it's actually conditionally stable. Okay, so I'm going to convince you of that, maybe. Okay, so just a reminder, what is the environmental lapse rate? Now here's where I get to actually, I've been warning you that when I said 6.5, this is the cooling rate for the environment as you're going up in the troposphere. For every kilometer you rise, it gets colder, 6.5 degrees. I said we need to revisit that, and we are going to revisit it now. Actually, sometimes going up, let's see if I have this last one. Sometimes going up in the atmosphere, doggone it, in the troposphere, in this layer, it instead of getting colder, it actually gets warmer. Okay, that's called a temperature inversion. And then you're definitely not at 6.5 degrees, okay? All right, so here we go.
Is that because of a high pressure settling over here?
There's different ways to get temperature inversions. That's one way. You can basically have air coming down and it's over colder air, and it's warmed and you have cold layers. So, but that's one way. All right, so here we go. So in this case, the environment is stable. Well, let's take a look. So notice that they sent up the weather balloon. Up there in the upper left-hand corner, it says that your ELR is 5 degrees Celsius per kilometer. Not 6.5, 5 degrees. Oh, okay, that's fine. So what does that mean? Now, in all of these figures, you read your ELR right over here. Okay? So what that means is it cools 5 degrees Celsius for every kilometer you rise. So it went from 25 to 20, and then went from 20 to 15. Now that is the environment. That's not our particle of air. That's the environment. Environmental lapse rate. That's what our weather balloon said in the ELR. Okay. So let's look at our chunk of air now. I don't see, it's nice and round. I don't see any clouds, do you? So it's all going to dry or cool, rise, expand, and cool at the dry adiabatic rate. So this says that you get a chunk of air going upward, and we talked about 4 different lifting mechanisms to get a chunk of air moving upward. So if it starts at 25, it's dry. It's going to go from 25 to 15, okay? And then it's going to go from 15 to 5, okay? It's all following the rules we talked about. No condensation is happening. It's the dry adiabatic rate. Now, let's look, and this is what we're going to do with the other couple of figures we're going to look at. If you want to know if this chunk of air is going to rise or not, you have to compare it with what the environment is. It's like your hot air balloon. It's called the hot air balloon test. I made it up. Okay. So here at, what is this, 1,000 meters, it's 15 degrees Celsius, and the environment is 20 degrees Celsius. So 15 is colder than 20, so it fails your hot air balloon test. Okay, this will not want to rise on its own. You can make it rise. It's stable. It needs to be warmer. This needs to be warmer if it's going to rise. This is colder. So this fails a hot air balloon test. It's stable. We could go up another 1,000 meters, okay? And up there we have a 5 degrees is our parcel, 5 degrees Celsius, and our air is 15 degrees Celsius. So it's like colder. It's like a brick. Okay, it fails your hot air balloon test. That's why we say actually we're showing you something here that is stable, totally stable. Okay, so that's kind of how these go. All right, so let's take a look at, so it's stable. Notice here on the right, we draw a down arrow because the tendency would be for it to go down. Why? Because it's colder than the environment. Tendency is to sink. All right. Last one. Okay. So I said we need to talk about absolutely stable, absolutely unstable, and conditionally stable, or something like that. We need to talk about those three. And in talking about those three, actually, if we come up with like a little equality, that should work for us. So this says, if the environmental lapse rate is less than the wet adiabatic rate, okay, I'm going to go ahead and draw that as an inequality, I guess is what you call it, right? So we're going to call this absolutely stable. Colon. Okay, your ELR is less than, this is where I would put this on my note card, is less than your WAR, and you just need to know what those are. Okay, environmental lapse rate, that's your environment. You send up a weather balloon. And your wet adiabatic rate, now here's where, don't blame me, but actually I'll put 5, but your author then changes it to 6. All right. So in that case, it's going to be what we call absolutely stable. And I'll kind of talk you through these last bullets. I think it really, if you look at a figure, it'll help you make sense of it. But at each elevation, basically, we're going to see as that chunk of air rises, it's going to cool faster than the environment. And if it does, then it's going to be kind of a situation we saw a minute ago, that at each elevation, it's going to be colder, so its tendency is going to be to sink. It's absolutely stable. And what kind of fun is that? The fun in meteorology comes when the atmosphere is unstable, right? Mm-hmm. Okay. All right. So here's your little picture. Okay. So what is the ELR? Well, I thought I had another figure here. Before this one? No, but coming next. Okay, good. I got them switched around. On the next figure, you can see me explain this. But I'll go ahead and show you what you're going to see is the wet adiabatic rate. I'll go right here. The wet adiabatic rate, even though I said it's set, we're going to go with 6 degrees Celsius per kilometer here. When condensation is going on, if your chunk of air is still rising, instead of cooling at the reduced 5, it's going to cool at the reduced 6 degrees Celsius per kilometer it rises. A few years ago, I looked this up, and actually there is a range for the wet adiabatic rate. So your author, he just should have been consistent. But do you see if we go with 6, which is what we're going to do in this scenario, if we go with environmental lapse rate of 5. Now what does that mean? So over there on the left you see what it means. When our weather balloon went up, if it started at the ground at 20 degrees Celsius, if it's cooling at 5, then it goes to 15, right? Cooling at 5 goes to 10, then it goes to 5, then it goes to 0, -5. Okay, so that's what our weather balloon said. That's what we need to compare our chunk of air with. So here we go. All right. So our chunk of air is going to rise, and actually you can already kind of see a little bit of clouds here between 2,000 and 3,000 meters, okay? But for the first few elevations, it cools at the dry adiabatic rate. So it goes from 20, no condensation, to 10, no condensation, to 0, okay? So right there at 2 kilometers or 2,000 meters, okay, we have condensation. Houston, we have condensation. Okay, so now it's not going to cool at 10, it's actually going to cool at 6. Okay, so now that's going to be -6. Okay, it's going to cool at 6. It's going to go from -6 to -12, -12 to -18. Why? Because condensation is happening. Okay, does that work? Yeah. So let's take a look at the balloon, the hot air balloon test. Okay, so yes, we compare the temperature of the parcel of air versus the temperature in the environment. So we have the same. So I don't know what to say about tendency there. It's like a wash. Let's go up one kilometer. What's that?
What does tendency refer to again?
Tendency means, is it going to rise or is it going to fall, sink? And I guess that tendency would be to say where it is. Okay, but at 1,000 meters, notice that we pass the hot air balloon. No, we don't. So 10 degrees. 10 degrees is still cooler. Oh, yeah. So this is cooler, okay, than this. And so it would fall, right? Tendency would be down. And here, it's cooler. Oh, yeah. Now I remember. These all fail the hot air balloon test. Okay? This is cooler.
Why would it still rise, though? I mean, even...
Well, why is it rising? What do you think? What kind of lifting mechanism is this?
Orographic?
It's not orographic.
Frontal?
I think it's frontal. It's frontal wedging. Wedgies? Yep. Frontal wedging. Yep. So these all fail the hot air balloon test. I know. Okay, and these actually, that's why the tendency is down, and that's why we say it is absolutely stable. Okay, and that's always going to be the case if it is less than your wet adiabatic rate. Okay? What do you think? Does that work for you? Okay. Let's go on to the next one. Okay, yep. Now, before we go on to the next one, and each of these like profiles, we're going to see something here on the right. The purple line, that steady purple line, is actually your ELR. This is your ELR. This is what the temperature of the air is doing. This right here is the temperature of your air parcel. Okay. The red simply means that actually it is cooling at the dry adiabatic rate, the DAR, and the blue means it's cooling at the wet adiabatic rate. That's what all of these mean. But in each case, do you see where it fails the hot air balloon? And this is always cooler. It's always to the left in this case, which means it's always cooler. Because down here we have the temperature scale. That's all that means. Okay, let's do the next one. Oh yeah, here's where I thought I was going crazy when I switched to this textbook and like went up against slides that used 2 different wet adiabatic rates. But my proof to you was this first one. This is what we did earlier, okay? And you can see that actually when condensation begins, it's cooling at 5 degrees Celsius.
So which one's the right one?
On a test, yeah, I know that's a valid question. On the test, I probably won't put you in that position. Yeah, I'm usually pretty careful, but there are 2 rates out there. So, or I wouldn't put you in that position, or whichever one you went with, I'd be cool with. So either that. But, and then here, this is the other rate, where it's cooling 6 degrees Celsius for every kilometer it rises. So, but you would think, putting together a textbook. So, anyway. So, the other one is absolutely unstable or absolute instability. So, again, we can kind of go over here on your note card. You could put absolute instability. Okay, and you could write it as an inequality, but this time you put the ELR is greater than, and the DAR is not controversial, the DAR. The dry adiabatic rate, no condensation happening, 10 degrees Celsius per kilometer. Okay, so if that's the case, then you're definitely going to have, your atmosphere is going to be unstable. Your atmosphere is going to be unstable. But that might be hard to do. It means that as you go up in elevation, it cools faster than 10 degrees Celsius per kilometer. But we have that happen. So what kind of lifting do we have here? Yeah.
Updraft.
Convection, localized convection. Yes, very good. Okay, so what your author did was to choose 12, which works for me. Okay, 12 is bigger than 10. So the ELR is 12. So what does that mean? That means if it starts at 40, 40 minus 12 is 28, minus 12 is 16, minus 12 is 4, minus 12 is negative 8. That's cool. That's the environment we need to compare our temperature of our parcel of air at. So notice for the first, looks like for the first 2 kilometers, no condensation happening. So it's going to cool at 10 degrees Celsius for every kilometer. So it's going to go from 40 to 30 and from 30 to 20. That works. We have the lifting condensation levels, about 2 kilometers, 2,000 meters. So now when it goes up from 2,000 to 3,000 kilometers, and I think we go with 6 here, okay, it's going to cool to a 14 degrees. Okay, and then it's going to cool 6 degrees beyond that, and so it's 8. So you see the tendency here is it actually passes the hot air balloon test when we check each one of these. So let's check them right quick. Okay. So of course 40 and 40, the tendency is a wash. Okay. But here finally, it's only by 2 degrees, but here finally at 1 kilometer, it's 2 degrees warmer. Okay. At 2 kilometers, it's 4 degrees warmer. Okay. When condensation begins, things really start happening, okay, because during condensation, energy is released, and so the chunk of air becomes more unstable. 10 degrees difference, and at 4 kilometers, we've got 16 degrees difference. So these all pass the hot air balloon test, okay? So in that sense, they are all warmer, and they will want to rise. And that will always be the case. We went with 12 here, but that will always be the case if your environmental lapse rate is greater than 10, or your dry adiabatic rate. Okay? Absolute instability. Absolutely unstable. So here's what kind of the profile looks like. Remember the purple line we said is what your weather balloon did. So that's your ELR. And the two kind of the segments here, this is cooling at your dry adiabatic rate, and this other one in the blue is cooling at your wet adiabatic rate. But in all cases, you see that the temperature of your parcel is always warmer than the temperature of the air it's rising in. So there you go. Pretty cool. So conditional instability, or conditionally unstable. So the one equality we didn't do yet actually is a 3-way inequality. So conditional instability. I'll try on the test to stick to these terms. Conditional instability. I'll try. Okay. So the 3-way is basically you put your ELR and you're like, okay, so I know I've got wet adiabatic rate and dry adiabatic rate. Well, the wet adiabatic rate is always going to be less, well, could be less, okay, and the dry adiabatic rate there Then all I gotta do is put my inequality signs, and to me, this makes most sense. Okay, put two less than symbols. So basically, your environmental lapse rate is larger than your wet adiabatic rate, and your environmental lapse rate is less than your dry adiabatic rate. So you don't have very much play in there for this conditional instability. So remember what this one is, 5 degrees Celsius per kilometer, or 6 degrees Celsius per kilometer, and this is 10. So let's see what your author did. So we have an example here. But it really struck me this semester, it's funny how you teach this for years, you're like, oh, that's how. It really struck me that the other conditional, is moisture. I'm going to put moisture question mark. Because actually, in the example we're going to look at is if you did not have a relatively moist parcel of air, I really don't think it would be even unstable, even having an ELR between the WAR and the DAR. I haven't entirely convinced myself of that, but I'm pretty sure. Okay. Because that last one talks about saturation being reached. So, and that needs to be a moist chunk of air. So here we go. So what your author did was he chose something between the two. He chose 9. He, she, they. So 9's pretty good. It's pretty safe. That's between 6 and 10. So with 9, then that means that this is the profile of the environment as you go up. So it starts at 40. 40 minus 9 is 31. Minus 9, 22. 13, 4. Negative 5. So that's what your weather balloon says. And that's what we need to compare a parcel of air against to understand whether it's tendency. All right. So actually, the lifting condensation level is drawn, it's hard to tell. It almost looks like it's drawn kind of between 2,000 and 3,000 meters. Right here. Okay. So when it first starts to rise, it's going to cool at the dry adiabatic rate. So for those first 2 units, we see it go from 40 to 30 and from 30 to 20. That's good. Now it's going to cool at the reduced rate of 6. Okay. So it goes from 20 to 14 and 14 to 14 to 8 and 8 to 2. Okay, so that's kind of what we've been talking about. We have the dry adiabatic rate here, the wet adiabatic rate there. So let's check it out. Let's do the hot air balloon test. So of course these are the same, so the tendency is flat. Okay, this one, it's 1 degree cooler, so this tendency, like this says, is to fall. Let's see. The next elevation at 2 kilometers, 2,000 meters, it's 2 degrees colder. So, I mean, these fail. These will not rise. They're like a brick. So finally, actually, and how do I say this? When we have condensation begin here, that's when we have a fighting chance of actually getting a little bit of passing the hot air balloon test. Because notice here that it's just 1 degree warmer. Okay, here it's 4 degrees warmer, and here it's 7 degrees warmer. Okay, so kind of a little bit of a mixed bag. Lower on, before condensation began, okay, its tendency was not to rise. As condensation begins, its tendency is to rise, yes.
So when they say you have a 40% of a chance of rain, then they're just calculating it like between the...
Yeah, when they give you the percent chance of rain, I'd say has something to do with this. The forecast, whether it's going to rain or not, they know what the environmental temperatures are and they know the moisture content. So there is definitely something to be doing, something to that. Okay, so this is a good place. I didn't want to get all the way. Awesome. So we'll start, actually, probably take a running go at it for this slide on Monday. Oh my gosh. So have a great weekend.